In this video, we're going to look at finding the derivatives of logarithmic functions, specifically logarithmic functions that are base e. So we are looking only at derivatives of functions of the form ln x. And so this is another one that becomes a little tricky to prove using first principles to you. In fact, the way we would normally prove this in a calculus class requires a skill known as implicit differentiation, which is no longer in the curriculum for Ontario, nor is it in the curriculum for SL Math. I can write a little proof here just to show how the derivative is found. However, if your interest in this is not robust, you can feel free to skip ahead. Once I'm done writing in this green box, we will be back proceeding business as usual. So to do implicit differentiation, you basically have to take that logarithm. We're going to rewrite it as an exponential. So if y equals ln to the x, then I know that x is equal to e to the y. Now the reason why that's helpful is because we just talked about how to take the derivative of an exponential function in a previous video. So if I look at this equation and I want to take the derivative, I'm going to take the derivative on both sides. I'm going to take the derivative of x. Now, because that's just 1 times x, the derivative of that is just going to be 1. On the right-hand side, it gets a little bit loopier because I know when I take the derivative of an exponential, the derivative is always the function itself times the derivative of the exponent. Now here the derivative of the exponent is a little bit weirder to find because the exponent here is y. And so my rules for taking the derivatives of functions in terms of x don't really apply the same way here that they would have in the past. So when I write down the derivative of that exponent, I'm actually just going to write the more general answer of dy by dx. And so that's that process of implicit differentiation where instead of finding an explicit derivative in terms of x's, I'm actually just implying a derivative. I'm saying the derivative of y is y prime or dy by dx. That's how I'm writing it out. It's not something concrete that you can get your hands on and plug an x value into, but you're going to actually see how this helps me out very quickly. Because if I now replace e to the y with what I know it's equal to, which is x, my next line looks like this. 1 equals x times dy by dx. And now if I just get dy by dx by itself, I get this. dy by dx is equal to 1 over x. And that's actually the derivative of ln x. So when I go to do the derivative of ln x, that's equal to 1 over x. And that is what would be in your formula booklet. And so this is the point where if you skipped ahead, we'll kind of pick up where we left off and just start doing some examples that use that rule of differentiation. Let's look at these two functions. This first one, y equals ln of x cubed plus 1. So this is a situation where I'm going to have to use chain rule. So when I go to take the derivative, dy by dx, it's the derivative of the outer function, so 1 over x, but with that inner function still in there, so x cubed plus 1. But then, because it's chain rule, I have to multiply by the derivative of the innermost function, which is 3x squared. Remember, the derivative of 1 is just 0. And so if I stick those pieces together, I end up with this, a fairly tidy derivative, I think. 3x squared over x cubed plus 1. Let's move on to the next one. F of x is equal to ln root x. So when I go to do the derivative here, I'm going to write 1 over root x, right, because it's the derivative of the outer function with the inner function still in there, times the derivative of that inner function, which I know some of you are taking root x and writing it as x to the 1/2, so you would probably write it as this when you do the derivative of the inner function. That can also be written out like this, 1 over 2 root x, if I express it with a radical again. If I stick it back together again, it becomes 1/2 times 1 over x, which I can just write as 1 over 2x. Now there's actually two ways to do this question. Because ln of root x can be rewritten as ln of x to the 1/2, and then I can use logarithm laws to bring that 1/2 out in front. This derivative could actually be a lot easier to find if I use this version of the function, because here, when I go to take the derivative, The coefficient out in front isn't affected by the process of taking the derivative, and I just need to take the derivative now of ln x, which is 1 over x. And that simplifies to be 1 over 2x really nicely. There's an important lesson here between these two strategies. The one on the left, while technically right, and it has you practicing chain rule and all sorts of stuff like that, it's not the most efficient. The situation on the right, I took a few more steps to simplify first, but the actual process of taking the derivative was much easier that way. Now that can be a really important lesson to remember when you're doing one like this. If you were to just use chain rule here, you're going to run into a little bit of an issue, because when I go to start taking the derivative, I use chain rule first, and so I'm going to write the derivative of ln 1 over x, but inside that ln, I'm going to put in x plus 1 over root x minus 2. But then, because this is also a chain rule situation, I have to multiply by the derivative of this inner function. If you don't already see where the issue is here, that inner function is a ratio of two functions. I'm going to have to use quotient rule. And so I then start to say, okay, the top function is x plus 1. The bottom function is root x minus 2. If I go to start taking derivatives of those, the derivative of the top function is 1. The derivative of the bottom function is nowhere near as nice because it is 1 over 2 root x minus 2. And so we basically then have to assemble those pieces back together using quotient rule, and it's just going to be a mess. Because here I'm going to have this big quotient rule write-up, and it's not even going to be nice. And it will simplify, don't get me wrong, but it won't be easy. You could go that route, and in fact, I'd honestly encourage you to just give it a try so you can actually see the distinction between these two strategies. But here's what I'm going to do. I'm going to take that function that we started with, ln of x plus 1 over root x minus 2, and I am going to use my logarithm laws to split it up, because I know when I have a ln of two things divided, I can split it up like this and write it as ln of x plus 1 minus ln of root x minus 2. And in fact, I'm going to go one step further, because I know that when I have a square root inside a logarithm, I can actually take that square root and write it as an exponent of 1/2, which I could actually then use my logarithm laws again and bring that exponent of 1/2 down in front. And now what I've done is I've actually taken the original function and made it a lot simpler when it comes to taking the derivative. Because now when I do dy by dx, for that first logarithm, it's just going to be 1 over the inner function times the derivative of the inner function, which is just 1. And for that second logarithm, that 1/2 is unfazed by the process of taking the derivative. I just need to focus on the ln of x minus 2. And the derivative of that is just 1 over x minus 2 times the derivative of the inner function, which is again just 1. And so now I actually have this fully simplified 1 over x plus 1 minus 1 over 2 times x minus 2. And then I'm pretty much done. I mean, you can simplify a little bit further. You can get a common denominator if you want. That's completely fine. It still is going to simplify quite nicely once you've put the pieces together here. And so if I just simplify on the top, I have 2x minus 4 minus x minus 1 all over 2 times x minus 2 times x plus 1. And that simplifies to be x minus 5 over 2 times x minus 2 times x plus 1. And then we're all set. So that's the derivative using log laws before you do the derivative. If you do the derivative first, it's going to be a mess. It will eventually simplify to be this. But I don't know that anybody wants to go down that path. And being efficient mathematicians, I think we want to get to the root of the problem in the most sufficient yet elegant way that we can. And so that's where we're going to leave this video. It should be fairly quick now for you to get to work on logarithmic and exponential derivatives. I think you'll actually find that these types of derivatives are fairly straightforward. If anything, the exponential derivatives are just going to have you practicing product rule, quotient rule, and chain rule. And the logarithmic derivatives, if anything, are going to have you practicing your log laws more than your derivative rules, which is kind of interesting. But it's all good practice because it's all prepping you for the final IB exam. So dive into those exercises. You should finish them up pretty quickly. And then we'll pick it up next time with trig.